Thank you. So I have a confession to make, actually. I don't like computers. I really don't like to use them. Of course, I do. I'm not a natural computational physicist and a magician like Norman is or Joel. Instead, I'm from a different kind of school of theoretical physics and theoretical astrophysics, kind of the Hans Bethe school, that use the results of supercomputer simulations as kind of data, as if it were an experiment. Okay? And then try to figure out how nature works based on that experiment. And this is kind of a morality tale, so I'm going to show you how that mode of thinking failed miserably. The real world is nonlinear, right? And the human mind, at least mine, is not very good at grappling with nonlinearity. So if I think about a linear system, what do we mean by that? Physicists kind of naturally try to think about things, they linearize systems so they can think about them simply. In a linear system, if you double some parameter in some model, then something else doubles maybe it doesn't. In any case, the response of the system to some kind of a perturbation is mild enough that you can control it and you can understand it. Nonlinear systems are not like that. So you may double some parameter and then find out that other parameters quadruple or quintuple or something like that. And more importantly, you may find that there is a completely unexpected phenomenon, something that didn't follow from your kind of linearized thinking, something completely new that you didn't expect. And that's what I'll talk about now. So I'm going to talk about actually a very surprising result, and you can see this down here, involving nonlinearity that was discovered with supercomputer calculations at UCSD and LANL, and mainly with these characters involved. So there are two parts to this. First, I have to tell you something about these mysterious particles called neutrinos, and then I'll tell you about the perfect engine for generating neutrinos, which is the collapse of a massive star. And then I'll get to my problem. My problem is trying to figure out how the neutrinos behave in these collapsing stars. So first, neutrinos. So here's the zoo of elementary particles, the building blocks of matter, the three families of elementary particles. Each family has a quark, up quark, charm quark, top quark, other quarks. Each family has a charged lepton, and the first family, the one you're probably most familiar with, is the electron. And then the second family, it's the muon, which is like a heavy electron, and the third family, the tauon, which is like an even heavier electron. Point is, we know the masses of all the particles on here except for these guys. These are all charged, they all have electric charge. These guys don't. These are the neutrinos, and each family has a neutrino, and notice that there are labels associated with them. So the neutrinos are a little bit like electrons in quarks in that they're spin 1/2, they're Fermi particles, but unlike those particles, the neutrinos have no electric charge. So hard to get hold of these guys. And each particle on this chart has some kind of an antiparticle. So for the neutrinos then, there are 6 known kinds of them. Electron neutrino, electron antineutrino, mu neutrino, mu antineutrino, tau neutrino, tau antineutrino. 6 of them. And these labels, the family labels, are called flavors. So here are the electron flavor neutrinos, the muon flavor neutrinos, and the tauon flavor neutrinos. Now, those flavor labels actually tell you how those neutrinos interact with matter. And as we'll see, the neutrinos that interact most strongly and are responsible for creating supernova explosions, for example, are only electron flavor. Although the supernova makes a lot of these guys, as I'll show you, as many of these guys, mu's and tau neutrinos, as electron flavor neutrinos, these are the only ones that really matter. And so if these kinds of neutrinos can convert into electron neutrinos, or the electron flavor neutrinos can convert into these guys, that give and take, changing one kind of neutrino to another, could in principle have a lot of leverage on the energy budget of a supernova, for example. Okay? All right. So we know the rest masses of all the particles on here. So for example, the electron has a rest mass. We say it has a rest mass of 500,000 electron volts. We like to measure masses of particles in energy units. Everybody's familiar with mass. Energy equals mass times the speed of light squared. So we like to measure the masses that way. The muon has a mass of like 106 million electron volts, and this guy's even heavier. And likewise, these quarks tend to get heavier as you move from the first family to the second and third families. These guys, we don't know their masses. We don't know the masses of the neutrinos, but we do know that they're incredibly light compared to any other particle on this chart, except for the photon, and gluon, which I don't want to talk about their masses because it's kind of meaningless. Okay. The neutrinos experience the weak interaction and gravitation. They're not charged, so they don't experience the electric force. So, and they don't call it the weak interaction for nothing. So at the typical energies of neutrinos that are created in stars in the early universe, the weak interaction is about 20 orders of magnitude weaker than the electric interaction that is responsible for how photons get detected in your eye, for example, or how atoms get ionized or something like that. 20 orders of magnitude, okay? So you've seen this statistic probably. You can look this up in lots of books. It says it takes a block of lead several light years thick to have a decent chance of stopping a neutrino with these typical energies, okay? So that's kind of, you might say, well, okay, great. So yes?
I'm sorry. What would be a decent chance?
Like of order 1. Okay? You want to shield yourself from neutrinos in the world. Okay? I don't know why you'd want to do that, but right now you're being bathed by about 10 to the 10 neutrinos per square centimeter per second coming from the center of the sun. Okay? All right. So you might even ask, how do we, with this, how do you even know these particles exist? Perfectly reasonable question. By the way, I'm never impressed by this statistic because lead isn't really all that dense on astrophysical scale. So, for example, the neutron star matter I'll talk to you about a little bit later, is 14 orders of magnitude denser than lead. And that can easily stop neutrinos, okay? As we'll see. So, well, it was Wolfgang Pauli's desperate remedy to save the law of conservation of energy in 1930. And the kind of quintessential weak interaction is beta decay, where a neutron turns into a proton by emitting an electron, which conserves electric charge, as a negative charge, the proton positive charge, and produces this electron antineutrino. So here's a cartoon of that. So back in the day, the experimenters could measure the mass of the initial parent nucleus and the mass of the final daughter nucleus, and they could measure the energy of the electron, the beta minus particle that came out, but they didn't know about this particle. And the energy difference between the initial neutron and the final proton is shared between this electron and this neutrino. Sometimes the electron gets almost all the energy. Sometimes the neutrino gets almost all of it. So once in a while, it looked like there was energy missing. And so the conservation of energy is something near and dear to physicists. So Pauli postulated there was an unseen particle that carried the energy away, carried away that missing energy. Nowadays, we don't think this is a very crazy thing to do because particle physicists do that all the time, invent new particles. But in 1930, it was really kind of desperate. And so here's a letter, which you can't read because of this. There's a German phrase here. Here it is. Verzweifelten Ausweg, a desperate way out. So in fact, this letter is written in a kind of a humorous way by Pauli to physicists who were experimentalists, actually, at a meeting he didn't go to, just kind of saying, hey, this is just a joke, but what if there was a particle that we couldn't detect and that moved out? Well, the particle was subsequently detected. Enrico Fermi, just a few years later, wrote down a simple theory for how the weak interaction works, and it's largely the way we understand the weak interaction to work now. So a lot of time has passed since 1930. Big machines and big detectors now detect neutrinos routinely, and we can say a lot about them. In the last 10 years, we've learned a lot from the laboratory about what neutrino properties are and how they behave. So here's a summary of what we know and what we don't know about neutrino mass. Okay? We know the differences of the squares of the neutrino masses from the solar neutrino problem and the so-called atmospheric neutrino problem, where this notation here is the difference of the squares of the masses. So one thing you'll notice is that these are very small numbers.
Maybe you should start by saying we know that all three neutrinos have mass.
Yes, we know that they all do, and right. And if I take the square roots of these numbers, it would give me a crude measure of the mass. You can see that that's like a very small fraction of an electron volt. Very small compared to the masses of those other particles. But we don't know what the absolute masses are. We don't know what these numbers are, okay? We don't even know what the ordering of the masses should be. So here's a cartoon to show you what the ordering of the masses might be. And there are really two ways we can do it that's consistent with the experiments that show one neutrino turning into another one, as Joel just described. So one is this one, the so-called normal mass hierarchy, where the heaviest ones are mostly mu and tau, like that. And then there's this doublet that's split by a small amount of mass down here. And the inverted mass hierarchy is where that doublet is on top. The experiments we can do on Earth can't tell the difference between these two. But it turns out that astrophysics, especially stellar collapse, is incredibly sensitive to which of these hierarchies nature has chosen. Okay? So our charge. What do these neutrino properties? Now, this is hard-won knowledge from the laboratory. So the laboratory scientists and the particle physicists had a simple question for us, the experts in theoretical astrophysics. Okay, what does this mean for astrophysics, cosmology, and supernovae? Seemed like a reasonably straightforward question, and it seemed like a reasonably straightforward answer. Nothing. Okay? And most astrophysicists said that it really couldn't do much because those mass square differences are so tiny compared to the high densities of material in a supernova, for example, that nothing really much would happen. Okay? Well, neutrinos do most of the heavy lifting in exploding stars, and it's largely because they carry the bulk of the energy and entropy in these environments. As we'll see, neutrinos can more than make up for their feeble interactions with huge numbers. That's the point. Although each individual neutrino doesn't carry much energy and really can't have much leverage on giving whatever energy it has to the environment, there are so many neutrinos created in a stellar collapse that it turns out they're of paramount importance. Okay, that might seem like a ridiculous statement, given that I told you that the weak interaction is 20 orders of magnitude weaker than electricity, but there are huge numbers. Nevertheless, we have to have really big detectors to see reactor, accelerator, and supernova neutrinos. Okay, here are several of them. Super K is 100 kilotons of water, for example, in a detector that's much like the detector that Brenda Dingus talked about a little bit earlier, but looking at much lower energy neutrinos. The weak interaction may be feeble, but it's the only means for converting neutrons into protons and vice versa. Now that's huge, because as you heard in many of the talks today, the core collapse supernova engine is the principal way that the elements, the intermediate mass elements like oxygen that are vital for life, for example, and the heavy elements, some of the heavier elements that are vital for life, like iodine, nobody mentioned that one. Those have to come from environments where lots of protons got converted into neutrons. Okay? Only the weak interaction can do that. If it wasn't for these neutrinos, basically you wouldn't be here. The sun wouldn't shine for very long at all. It would be long extinguished. Okay? And there'd be very few of the elements required for life. Okay? So the sun is a nearby fusion reactor, and the red ones are protons, the gray ones are neutrons, and the fundamental interaction is to take two protons and turn them into a deuteron, a proton and a neutron. So there's a fundamental issue here. You have to have the weak interaction or stars don't shine. At least they don't shine for very long. There's a spectrum of them, of the neutrinos. Take a picture of the sun in photons. This is in X-rays. Take a picture of the sun in neutrinos. This is made with Super K. It isn't a very good picture. Really, this should be a point. Claire, this is where you have to come in. You need next step, adaptive optics for Super Kamiokanda. By the way, the Japanese head of this experiment, Koshiba, famously was asked by the Japanese Science Foundation why this picture wasn't round, and he, the claim is that he said that if you give us more money, I can make it round.
Actually, George, is that pointing out that this is taken through the Earth?
Yes, that's true. This is taken at night, right? Okay, but so Whereas neutrinos are innocent bystanders in the sun. They don't do anything other than tell us there were nuclear reactions. They don't play any dynamical role. They don't deposit any energy in the sun. They're the criminal masterminds in core collapse supernovae. Okay, so let's talk about that. So stealthy neutrinos undermine the financial stability of massive stars. They set up the conditions that guarantee the collapse of these stars. And in so doing, they create the perfect engines for generating titanic numbers of neutrinos. And when I mean titanic, I mean like 10 to the 58 neutrinos. That's 10 times the number of protons in the sun, all in a span of about a few seconds. Okay? So these neutrinos then bring about the explosions that seed the universe with the elements necessary for life, et cetera, et cetera. So what does a star like this look like? This is from a Scientific American article in 1987 by Tom Weaver and Stan Woosley. This is luminosity of the sun, luminosity in thousands of times the luminosity of the sun here. And so this is 25,000 times the luminosity of the sun. This is the surface temperature in typical astronomy fashion, plotted the wrong way. And so this is kind of an evolutionary plot of the best fit star that was the progenitor of the supernova 1987A explosion in the Large Magellanic Cloud. You can see it lasts for about 11 million years and then winds up becoming a supernova. Okay, and there are various stages of nuclear burning. Here's a table. First stage is like our sun right now. It burns hydrogen to helium. It's somewhat hotter than the center of the sun. Astronomers like to measure, astrophysicists like to measure temperature in units of energy. So the center of the sun, for example, is about 10 to the 7 Kelvin, 10 million Kelvin, about 1 kiloelectron volt. This 25 solar mass star is about 5 times that. Likewise, the density of the center of the sun is 100 grams per cubic centimeter. This is only 5. Okay? Nevertheless, the sun will spend something like 10 billion years burning hydrogen. This will spend only a few million years burning hydrogen. You notice that in the ashes of hydrogen burning are helium, and it'll spend a million years burning helium. You'll notice that there's a fantastic acceleration in the rate of burning of one set of ashes to the next stage from core carbon burning on. Here's why. Remember, this is almost a million years here, but this is only 600,000 years. And these burn in a year or a few months. What's that? 600 years. And this is much shorter than that. And oxygen burns to silicon in about 6 months. Silicon burns to iron, the peak of the binding energy curve, in about 1 day. So what happens here? The answer? This gets hot enough that now neutrinos are being created copiously and emitted from the centers of these stars. And in fact, from here on, the luminosity of the star is in neutrinos far exceeds the luminosity in photons coming from the surface. Yes, the luminosity is the energy per unit time that comes off. So the neutrinos are carrying the energy away. So it's as if you have this big bank account. And the bank account here is that the star says, I'm good. I've got lots of hydrogen fuel, and I can burn that all the way to iron. And I can get a fair amount of energy out of that. What you don't know is your bank is buying, I don't know, securitized bad mortgages or something with your money. Okay? So in this case, the bank is buying neutrinos, and the neutrinos are leaving and taking away the deposits of energy. And so the core is actually getting colder in a thermodynamic sense. Oh, you say, well, wait a minute, that's not true. The temperature is going up. Look at this. Not true. So the only equation you'll see in this talk, this is on Boltzmann's tomb, by the way. This is entropy. It's a measure of the order or disorder in a system. So high entropy is where lots of particles are flying around helter-skelter with lots of degrees of freedom. Low entropy would be taking all those particles and jamming them, forcing them into moving together. So there are fewer degrees of freedom, like taking all these neutrons and protons and turning them into a carbon-12 nucleus, for example. So that's what's happening here. Massive stars are giant refrigerators. So from core carbon oxygen burning onward, the rate at which neutrinos take energy away is far exceeding that of the photons. So the neutrinos carry entropy out of the core. They're making the core far more thermodynamically cold and ordered. Okay? So the entropy in some units goes from about 10 down to about 1. the entropy per atom in this room is about 10 units of Boltzmann's constant. Okay? That's the same number in the center of the sun, really, roughly. But in the center of these stars, it's more like 1. So that's what I mean. It's thermodynamically very cold. And what that means is that the pressure exerted by nucleons, by ordinary atoms, is relatively low. And so the electrons have to provide the pressure. They can do that by being jammed into a small region and moving near the speed of light. And that sets the star up for instability in general relativity. Gravity loves a situation like that because it can pick the star off pretty easily. It's unstable. In fact, when the star starts to collapse, it's essentially a frozen crystalline solid. Okay? Even though its temperature is 1,000,000 electron volts, 10 to the 10 Kelvin. All right, so that's what it looks like at the end of its evolution. This iron core is about the mass of the sun. And here are some things to scale here. The iron core itself, although it's got the mass of the sun, about the size, the physical size of the Earth. 10 to the 8, 10 to the 9 centimeters in diameter, something like that. Okay? Is that?
Like a white dwarf.
Yes, like a white dwarf. It is a white dwarf.
Exactly.
Yeah.
I wanted you to say that because people would probably they've heard of that, so they would better understand.
Yes, it's effectively a white dwarf. Any star supported by the Pauli principle force of pressure from electrons is we call a white dwarf. And effectively, this is a white dwarf, although it doesn't look like the usual white dwarfs one sees lying around the galaxy, because this one is awfully hot in terms of temperature, T, although thermodynamically cold. So this thing collapses, and to put this in perspective, once this core, the size of the Earth, mass of the sun, goes unstable, it will collapse near the free fall rate, as if gravity almost wasn't there, as if pressure wasn't there. It'll fall in about 1 second to a radius of about 30, 40, 50 kilometers, something like that. And within another second or two, it'll be the size of Greater Santa Cruz, something like 10 kilometers across. Okay? So that's what we're talking about, collapse of something the size of the Earth, mass of the sun, in 1 second, basically to a neutron star. Okay? So if I think of the optical kinetic energy that comes out of a supernova explosion, it's about 10 to the 51 ergs. Okay? But the total, right, that's the explosion we see, but it's only 1% of the energy that comes out in neutrinos. The total energy released in neutrinos is 100 times this. Okay? And that's a prodigious amount of energy. It's about 10% of the rest mass energy of the star. Remember, that's a solar mass. So I take the mass of the sun and multiply by speed of light squared. That energy is about 10 to the 54 ergs. And we're converting about 10% of that into neutrinos. And that's about 10 to the 58 neutrinos, because each neutrino carries about 10 million electron volts of energy. We can get these numbers just by looking at the gravitational binding energy and going and collapsing from something the size of the Earth down to a neutron star. And the only time scale in the problem is really the time it takes. The neutrinos are trapped inside this collapsing thing. And if you ask the random walk time, for the random walk time of these neutrinos to get to the edge, it's about a few seconds. Okay? And they're roughly all 6 neutrinos are involved in this, so it's about 10 to the 51, 52 ergs per second in each of the 6 kinds of neutrinos. Again, the only ones that really matter, though, that couple in some of the energy, are electron-flavored neutrinos. So this is the picture we have. You make this proto-neutron star. The neutrinos diffuse inside of it, but when they get to the edge of it, they decouple more or less and freely stream, that's what these pink arrows are, outwards. But if you can capture about 1% of the energy of the neutrinos in this mantle out here via these processes that involve only electron-flavored neutrinos, then you can create a supernova explosion. In fact, convection in the neutron star can aid that, and supercomputer simulations show that that might be possible. More importantly is that convection and hydrodynamic motion can transport the energy that tends to be deposited closer to the neutron star and neutrinos outward to where the shock wave is and blow the star apart. But notice that it's electron-flavored neutrinos that do the dirty work. There's our favorite picture, the Crab Nebula, the result of this process. And if you don't believe that supernovae explode, I can tell you that they do. Here's a picture of, there's a star you can find there. I used to know how to find it. And then it exploded one day in February 1987. And the neutrinos from it were detected. And only 19 of them in these two experiments, although the number of papers written on that is probably exceeds that by a factor of 1,000 or so. I don't know. Okay. We didn't learn much from this as far as particle physics go, but the basic picture I showed you of collapse of that Earth-sized configuration to a neutron star, as Joel said earlier, is completely confirmed by this. There's no other way we could get those neutrinos. Okay? So now, let me talk about how neutrinos change their flavor. Each neutrino can be regarded as a quantum system. I have to tell you a little bit about quantum mechanics. In quantum mechanics, you may know, a system can be in two or more seemingly mutually exclusive states at the same time, right? Schrodinger's cat is both alive and dead till you measure it. And neutrinos, each neutrino that's emitted from that neutron star can be much the same way. It could be in different flavor states. So as it propagates along, a neutrino can be in one of these quantum superpositions of different flavor states. Interestingly, the medium around that neutrino can influence the relative mix of those flavor states. So our charge as theoretical astrophysicists is to figure out how the medium changes that mix and whether neutrinos can change from mostly one flavor into another and how that works. Okay? Here's the really weird hook in this. Some of the medium, I just showed you that 10 to the 58 neutrinos come out of this supernova. So as take one neutrino and you ride along with it, a lot of the medium that it's moving through is neutrinos. It's seeing other neutrinos. So here's the problem. Some of this medium consists of other neutrinos, and the upshot is that how a neutrino changes its flavor depends on the flavor states of the neutrinos. It's nonlinear. Okay? So let's say that I wanted to know, here's our neutron star, and it's emitting neutrinos from its surface copiously. They more or less freely stream out. Let's say I want to know the flavor evolution of that neutrino. I want to know how it changes its flavor as it moves out. I need to know the flavor so I can tell how it interacts. Okay, and there's another neutrino that comes along. Now, the flavor state of this neutrino is influenced by the flavor state of this one that it scatters on. When I say scatter, I mean forward scatter in the way photons move through a lens in a glass lens in a camera or your eyeglasses. It doesn't absorb it or change the direction. It just changes the properties a little bit. So now these two neutrinos influence each other quantum mechanically. There's another neutrino. Now this one influences this guy that influences this guy that later comes back and influences this one again. So you can see that this gets very complicated very quickly. Okay? So to solve this problem, we have to do it on a supercomputer. And roughly what we're talking about is solving something of order, I don't know if you can see this, but something of order millions to of order 10 million coupled nonlinear partial differential equations. Now, you might even wonder why we even bother to do this, since the simple answer is that because the densities are so high in the supernova, you can't really get anything to happen. Let me show you. By the way, I'm going to show you a movie now. Notice that these neutrinos move in different directions. The directions are set by that angle right there. And when I refer to radial direction, I mean something moving directly out. And a tangentially moving neutrino would be one that's tangent to that neutrino sphere. Okay? So I'm going to show you a busy diagram here. This is neutrino direction. And the horizontal axes are all neutrino energies. And the typical energies of neutrinos are about 10 MeV. Neutrinos on this side, antineutrinos on this side. Here are the spectra, the energy spectra, relative energy spectra of two different types of neutrinos. Red is electron flavor. Blue is mu and tau neutrinos. Okay? And these are antineutrinos here. This is a color code. And blue means the neutrino has changed its flavor. It started out as, say, one flavor, say a muon neutrino. And if it's blue, it changed to another flavor, electron in this case. Okay? So red means nothing has changed. Blue means something has changed. Neutrinos on this side, antineutrinos on this side. This direction is this. 1 here means that the neutrino is moving directly radially outward. 0 means that it's moving tangentially. Okay? And this blue bar down here tells you how far away we are from the supernova. So what we've done is to calculate the neutrino flavor field, and what we're going to do is pull back slowly from the neutron star. Okay, and that blue bar will tell you how far we've gone, and these are in units of 10 kilometers. So there's 50 kilometers right there, there's 100 kilometers, 150, 250 kilometers. Here's roughly what the geometry looks like. Okay? So now this calculation is one that uses the normal neutrino mass hierarchy, that first one I showed you, but does not include the nonlinearity. This was our zero order answer, more than zero order in many cases, that nothing really happened. Okay, so I'm going to start this movie, and we're going to pull back. You can see that this bar is moving out. Okay, and very low energy neutrinos are transforming, right? This blue thing is creeping here. Antineutrinos, nothing's happening. Nothing happens. Okay, let's do the same problem now and put the nonlinearity in. Okay? So we're moving out, slowly moving out. You can see that this starts to look sort of the same and then suddenly doesn't look the same at all. Let me stop it right there. I'll freeze it at something of order 80 kilometers, and you can see that this looks nothing like the case that left out the nonlinear effective neutrino coupling to neutrino. What happened? Look at this. All the electron neutrinos in lots of different directions and essentially all energies, and most all the antineutrinos have transformed their flavors. Totally different. Completely different. And I can let this go on. And you can see that there's this rich interplay of quantum interference that's going on. And if you look here, you can see this kind of collective oscillation. In fact, what's happening is that all the neutrinos together, they're cutting each other up. They're crossing each other's paths, and so they're all informing each other what flavor state they're in. And so what happens is that all the neutrinos are collectively changing flavor in the same way. We call these collective neutrino oscillations, and we did not expect to see anything like this. Okay? I could do the same problem now, but now in the inverted mass hierarchy rather than the normal mass hierarchy. Remember, we can't tell, nature, at least experiment, can't tell the difference between these. Notice that this one is violent. There's no weighting. And the reason is that the neutrino flavor field is essentially unstable in this inverted mass hierarchy. It wants to change. It wants everything to change right now. Okay? And so you can see we get the same collective oscillations, but they look qualitatively quite different. Anyway, let me cut to the chase. So here's what we would get. Same kind of thing. This is the direction of the neutrino. You know, tangential here, radially outward here, energy in MeVs here, okay? And neutrinos on this side, antineutrinos on this side. But now these top panels are for the normal neutrino mass hierarchy, the bottom panels for the inverted neutrino mass hierarchy. And if I could direct your attention to the neutrino panels, you'll see that these are almost the mirror images of each other. We call this, in fact, the spectral swap. You can see that in the normal mass hierarchy, all the low energy neutrinos below about 10 MeV here transform their flavors, and not many of the higher energy ones. But in the inverted mass hierarchy, it's exactly the opposite. The low energy ones don't, they stay in their original flavor states, and pretty much all the high energy ones transform. So as I told you, supernovae are incredibly sensitive to what mass hierarchy nature has chosen for the neutrinos. Yeah. Yes, excellent question. So the one that was the linear variety, we just had a static background of protons and neutrons and electrons and nuclei. Okay, and we didn't have any neutrinos in the medium. We didn't allow the other neutrinos to influence, to be part of the medium that determines how neutrinos change their flavors. Okay. We're actually grossly complicating those equations and coupling them together in a way that we're not in the linearized version, correct? Okay? Which is physically correct. I mean, you can't leave them out, really. You mean in a theorist's mind and in a supercomputer simulation, you can do these experiments. And you could say, what if the world really did look linear, like we thought it did? Okay? And you find out that the answer you get is just crazy. It looks nothing like the phenomenon you see in the real world. Okay?
But can you put in enough variables to actually measure the reality then?
I'll get to that in a second. Okay? By the way, those calculations I showed you, these are done for the late times in these supernovae, something like 3 or 4 seconds after this collapse. And the reason we do that is because that's after the explosion. And a lot of the matter has been driven away by the explosion. And so the neutrino part of the medium has a bigger purchase on turning neutrinos from one flavor to another. Okay? So we know, we're pretty confident, and there are many modelers around the world now who are doing the same kinds of calculations and get the same phenomenon. So we're sure of this, we're pretty sure as we can be that this kind of spectral swap phenomenon is there, at least for late times. If you want to do it at early times, it's very difficult. And the reason is because the matter densities are even higher there, and the neutrino densities are even higher. So here's one, and I'll just show you. This is kind of a different thing. Again, same kind of, this black means no flavor transformation, white means no flavor transformation, direction the same way, energy here, but lots of different kinds of spectra. So here I plotted different kinds of neutrinos. Now this includes all 3 neutrinos, not just 2. And so I'll just show you this one. This is for an early time calculation. This is for the so-called neutronization burst, when the shock just comes through the surface of the neutron star. You can see the same kind of phenomenon develop here. You can see these collective oscillations going here. You can see that I get the swap here. In fact, now since there are 3 neutrinos, there are 2 swaps. There's a swap there and a swap there. Everything transforms at this radius. There's the radius bar down here. And we end up picking up something that looks very much like I showed you before, a little more complicated, but there's the spectral swap. Okay? All right. So I can understand, now that I know the answer, theoretical physicists are really good at this sort of thing. Okay? So now that you know the answer, we can explain it. Okay? So, in fact, it's not even so surprising once you know the answer. It's like the joke about the mathematician that sits there for like 3 months working on some problem, and then finally sits up and says, oh, it's trivial. Okay? So we can understand this, and one way to do it is by looking at other kinds of systems with spin. So we can invent a kind of spin for a neutrino flavor. And just say that there's a kind of a spin. It's not the real spin, but the direction of the spin gives the flavor. So if it's pointed up, it's electron flavor. It's pointed down, it's some other flavor, mu or tau. And if it's pointed sideways, it's some quantum mixture of both of them, like this. And the analogy might be magnetic spins of atoms. Atoms have like electric currents and the electrons flowing around, and so it's like a little magnetic moment for an atom. And this is a well-known thing. If you go and talk to your condensed matter physics colleagues, they'll tell you all about these kinds of things. They have a well-developed technology for dealing with this. Okay? So if you go and talk, if you're on speaking terms with your condensed matter colleagues, you can go and, the astrophysicists are laughing. You can ask us about that later. I could think of a ferromagnet. And at very high temperature, the actual real magnetic spins are pointed helter-skelter everywhere, perhaps. And then if I cool it down, and usually they talk about going the other way. Because if I cool it down, the spins will start to line up for energetic reasons. Okay? And they'll line up into domains. Maybe they point all up in this case, and they form a nice bar magnet, North Pole, South Pole. And over here they have the same kind of orientation. But there might be another domain where the spins point in a different direction. And we can understand the formation of the flavor swap in this way. This kind of helter-skelter thing is where there's a lot of complicated collective oscillations going on. But as we move further and further from the neutron star, eventually there's a kind of a freeze-out where the neutrinos don't see so many other neutrinos anymore. And we then start to line up in spin domains, much like a ferromagnet. It's a very close analogy, actually. So now we can understand it. But my point was that we didn't even know this phenomenon was there. Maybe if we were better physicists, we could have figured out that it was there, but nobody did. Okay?
Until they ran.
That's right. Until they just gave up on trying to ferret out the answer with human logic and intuition, and instead just coded it up and did it, brute force. Now, you couldn't do that very easily because that calculation I showed you was 7 million nonlinearly coupled PDEs. That requires a supercomputer. Okay? So here's roughly what happens. That's what causes these spectral swaps. In the magnetic case, you cool it and the magnetic spins line up. We see this all the time. And in the neutrino analogy, the cooling, moving away from the neutron star, causes the neutrino spins that give the flavor, because there's actually an energy associated with the direction of those spins to line up in domains in energy space, not physical space like this, but in energy space. Okay. So, couple things. Who cares? All right. Well, it's possible we could detect a supernova neutrino burst. After all, one was detected from a supernova in the Large Magellanic Cloud. That's 50-some kiloparsecs away. If we got a stellar collapse in the galaxy, it'd be 10 kiloparsecs away. So that will give a whole lot more neutrinos. Moreover, the detectors we have online right now are bigger and better, and the ones we envision are much better at resolving neutrino flavor and energy. So in principle, we could detect those swaps. If we saw those swaps, what would it tell us? Immediately, right off the bat, it would tell you what the neutrino mass hierarchy is. Now, that's a quantity that's sought after in neutrino accelerator experiments right now, but the prospects for measuring it are dicey for funding reasons and for technical reasons with those experiments. Anytime you're dealing with neutrinos, you're kind of on thin ice, okay, because it's very hard to detect them, as I just said, even in particle accelerators where the energies can be quite large. So, but other than particle physics, what you saw was that what happens as a function of time in the supernova with the flavor changing really depends on conditions in the supernova. So, for example, as the shock wave moves through, that will modulate the way these neutrinos change their flavors. And in principle, if we could get the neutrino signal, we could watch that shock wave move out. We know how strong it was. We could see it being re-energized. Okay? All right. Maybe you don't believe we'll ever have enough funding to build a decent neutrino detector to see a supernova, or maybe you'll think there's not going to be a supernova in your lifetime in the galaxy. I don't know. If you do, still there's importance in this, because remember, it was the neutrino interactions that deposited energy and drove the explosion were flavor specific. So if we know how the neutrinos change their flavors, it can give us insight, better understanding of how you even get these explosions in the first place, or whether we even do in all cases. It isn't clear that all stellar collapses result in explosions. In fact, maybe only half or something like that. So that's kind of interesting. So I'll leave it there. Yeah. Well, because, again, just like in the supernova, the detector medium is flavor sensitive. So electron flavor neutrinos have an advantage over mu and tau flavor neutrinos because there are more ways they can interact in the medium. Why is that? Because when electron neutrinos are absorbed by an atom, by, say, a neutron in an atom, they make an electron in the final state, okay, or a positron. Okay? That energy, the mass of that electron or positron is modest, half a million electron volts, small compared to the energy of these neutrinos. But if I have a muon neutrino, I can have an analogous process, but that process has to make a muon, which is 100 MeV, okay? 10 times the typical energy of the neutrinos that are coming from the supernova. Yeah, right. So that these particles have different signatures in these detectors. Okay, so that's the short answer. The more complicated answer is it depends on the detector medium. So, many of the particle physicists who are agitating to build detectors to do neutrino oscillation experiments, for example, they have a different agenda than we astrophysicists do. So, for example, we might like them to build their detectors out of liquid argon. Why? Because liquid argon is almost ideal for detecting these kinds of flavor swaps. Whereas the alternative, water, as in the water Cherenkov detectors that Brenda talked about earlier, are not so good for detecting the flavor swaps. Unless they're, yeah, that's right.
Sadly, one of those that
The one that we had is no more. Right.
given back the Canadian can-do.
That's right.
I was going to ask a similar question about how, what's the difference between astrophysical neutrinos and solar neutrinos and the types that, I was thinking of that CERN experiment, faster than light, that were not faster than light.
I was hoping no one would bring that up, but
They're looking at this flavor swapping, right? And then they noticed this odd signal that they thought was faster than light. But is there a difference in how that occurs in that type of neutrino or in solar neutrinos versus these higher energy?
yes. So the length scale over which the neutrinos change their flavors is proportional to the energy. So the higher the energy, the longer the baseline on which you have to operate in order to detect the neutrino having changed. Okay? So, and the energies of the neutrinos that you're talking about, for example, and that we're talking about for example, for the long baseline neutrino experiment, which the United States is proposing to build between Fermilab and the underground lab in South Dakota, those energies are of order 100 times the energy of these supernova neutrinos, right? That's why we need a very long baseline. We need of order 1,000 kilometer long baseline to do that. Now, that baseline, that length scale over which they change, is also inversely proportional to the mass squared, that mass squared difference. Okay, so you can use shorter baselines to look for new kinds of neutrinos. What is that? So I mentioned the three that we know about. Those are the three that have ordinary weak interactions. If there are any other kinds of neutrinos, they generally go under the heading of sterile neutrino, and they can't have ordinary weak interactions. We know that. And there are claims for having detected some of these. Somebody mentioned that new things in science are always at the 2.5 or 3 sigma level. These are always at the 2.5 or 3 sigma level, which is why nobody really believes it. But nevertheless, it's interesting. It's plausible that they're there, but we couldn't detect them the same way. They're even harder to get. But at higher energies, because they have mass squared differences that may be much larger, even at the higher energies, we can look on shorter baselines. Okay? Note that.
So does this change the interpretation of any of the detections that have been made so far, like in Supernovae?
Oh, that's an excellent question. You mean of the 1987A detection?
What does it mean for one?
If I could find that slide again, you can't possibly, but you can say very little from 19 events. The statistics, the numbers are just so small that it's hard to say anything about them. So people, for example, have said that there are lots of neutrino detections here at less than 1 second. So those are probably electron neutrinos from the neutronization burst. Okay, there are a number of papers that say things like that, right? But the neutronization burst lasts for 10 milliseconds. And moreover, the mix of neutrinos and other kinds, electron flavor and other kind of flavors is not as big as you might think sometimes in some models. So we really can't say very much there. This gives 19 events, but we're talking, if we had a galactic supernova, a core collapse supernova with the kind of detectors that exist now, like Super K, and maybe a fairly large liquid argon detector, we're talking about many tens of thousands of neutrino detections, not 19. Okay, so we could say a lot more. We'd have a much better time sequence of neutrino emission. Okay? So I guess my short answer to your question is can't really get much out of this because there are so few events, right? All we can really do is look at it and say, is my model totally inconsistent with this? That's about it.
I'm sorry, maybe if this is too convoluted, you can talk with me afterwards, but I'm still trying to understand how you couple these interactions. You have 7 million equations, one for each particle, or one for each neutrino.
Well, not really.
7 million variables.
No, we have a lot more neutrinos than that. Those are the bins, okay? We have something like, when you look at essentially the binning we have, it's equivalent to something of order, 7 or 8 million. We have to follow angles, so we have bins of angles and also radial zones like shells. Yes, right. Yes.
And then you have an equation then for each bin.
Yes, effectively.
And you solve all of them.
Right. So very much like those fluid mechanics equations that Mike wrote down earlier on, except they're unlike that because they're not F equals ma. They're not kind of classical hydrodynamics. They're actually more like the Schrödinger equation that governs how electrons move in atoms. In fact, they really are a Schrödinger equation, okay? Because this is a quantum mechanical system.
Maybe worth emphasizing that they're not a bunch of free parameters for each of these 7 million.
No.
They're well-posed, well-known. It's a well-posed calculation, not like what Greg was working on was talking about, tons of free parameters. That's not the issue here, it's just very hard to solve.
That's a good point.
Back when you and I and Chad wrote that paper about the possibility of inverted hierarchy,
Yeah.
which may have been one of the first papers on
It-
inverted hierarchy.
It was considered idiotic to think about inverted mass hierarchy.
What we were worried about was having too many neutrinos that would drive a region to be neutron poor rather than neutron rich. As you mentioned right at the beginning of your talk, it is essential for the R process to
Right.
have a very neutron-rich region above the neutron star.
Right.
So you must not have the neutrinos drive those neutrons into protons.
That's right.
Any effects with the two different schemes, inverted or regular, that have to do with the production of the heavy elements? You didn't mention that. I was kind of waiting for that to come out of your calculation.
We don't know enough yet. We're only taking baby steps at this point. I mean, sophisticated as this calculation was in terms of kind of pushing what one can do, it still was a spherically symmetric model. Supernovae are manifestly not spherically symmetric, even at high density. Okay, so it was a simplistic model that way. Moreover, with other kinds of physics that was simplistically treated. So so I don't think we're at the stage yet whether we can say something about that's our intent, is to be able to say what happens, how this kind of flavor transformation feeds back on the explosion physics and on nucleosynthesis. Now, I think what we said in that paper is still true. The inverted mass hierarchy still is maybe not, it's funny. If I could show you.
Was our paper the first paper that discussed the inverted hierarchy?
Probably was.
I don't remember any other one. I remember I cooked it up on a sort of, a dare.
Right. And I think there's nothing, particle physics-wise, there's nothing wrong with the inverted mass hierarchy. The word inverted in English seems, as opposed to normal, makes it sound like there's something not normal about it. But right. And I should point out that every property that particle physicists have predicted about neutrinos, when confronted with experiment, has been incorrect. So, so there's hope, Joel. I mean, we might have been right after all. But you can see that you're converting these higher energy mu and tau neutrinos into electron neutrinos at higher energies. Okay? So again, that's like what we said in that paper, in that you're going to have more high energy electron neutrinos. They can capture on neutrons and destroy them. But the question is, it's always critical where this is happening. So maybe this isn't quite the right place. Okay?
Was it through neutron detectors that we determined that they were actually exchanging mass, changing flavor?
Changing flavor.
Yeah.
It was, yes. Okay, so
And that was obviously a big deal.
So that's a legitimate experiment.
right,
Three different ways.
yeah, right, yes. Mhm.
Nobel Prize. Not for the Sudbury experiment. I think it's worth Donald and his colleagues getting a Nobel Prize for the Sudbury experiment.
Yeah,
The
the,
experiment that got the Nobel Prize was the Davis experiment, which Bacall should have shared, and of course Toshiba for Supercomputers.
right. It was for the development of the probes themselves rather than the scientific result. Hmm?
But the experiment really proved for the first time that you have this oscillation, and that the 2/3 of the neutrinos of the sun that we thought we were missing are actually there, but they were the other two kinds of neutrinos. That's the Sudbury experiment, and I think that's worth the Nobel Prize.
I agree. Hmm?
You mentioned inverted mass hierarchy a number of times. What exactly?
Just, these are just words because we don't know what the actual ordering of the masses is and the way the flavors are distributed with those masses. So I don't know why I've lost the signal.
Actually, let me say it very quickly because it's really a simple idea. The level of the masses, the order of the masses of the charged electrons is, of course, electron, muon, tau. The electron being, neutrino being, the electron being much lighter than the muon neutrino, the factor of 100. And then the electron neutrino is the lightest, the muon, sorry, the electron is the lightest, the muon is the next lightest, and the tau is much heavier. Okay? And so we would naturally assume that the order of the neutrino masses is the same, with the electron neutrino mass the lightest, the muon neutrino mass next, and the tau neutrino mass on the top. But, as George said, everything we used to think about neutrinos, for example, if they're massless, has turned out to be wrong. So why make the obvious assumption? Why not consider alternatives? If you put the order exactly the opposite, you get the inverted hierarchy.
I'm trying to show the hierarchy.